Alright, next up we're going to talk about modern solid-state drives. And solid-state drives are sort of interesting devices. What they do is they simulate hard drives, and they simulate hard drives by storing the data on NAND flash. And especially for SATA SSDs, which are the things that look like traditional hard drives, traditional laptop hard drives, they spend so much effort simulating hard drives that they end up inadvertently simulating some of the performance limitations of hard drives. For example, a SATA SSD has noticeably better sequential performance than random access performance, not because the flash hardware requires that, but because the SATA interface that's allowing the solid-state drive to interface with the computer was designed for hard drives where obviously that was true, so there was no reason to sort of optimize the protocol for the random access case. When we're talking about NVMe or PCI, those are the same devices. SSDs that go directly on the PCIe bus, they end up having sort of performance that's more related to the underlying NAND flash and less related to the protocol that was designed for hard drives. But we do still have some performance constraints as a result of the flash memory itself. Now, reads and writes are pretty fast with NAND flash. If we're talking to the flash chips themselves and we want to do a read to read like a 4K block or a 512 byte block, whatever it ends up being, again, we're using logical blocks the same way that we did in hard drives. The latency to read a block is going to be something like 25 microseconds. And the latency to write a block is not drastically slower. Alright, it's like 10 times slower at 200 microseconds. But if you do out the math on this, this isn't the bottleneck in most of the stuff. Like, the difference here between read and write latency isn't the problem, especially since for larger I/O operations, this can happen in parallel across multiple blocks of memory on the SSD, multiple flash chips on the SSD. We really aren't constrained that much by the sort of I/O latency compared to hard drives. Compared to something like DRAM, which is really fast, flash memory is still kind of slow, but reads and writes are pretty quick. The big complication that we have is that writes are slightly complicated. And it's not because writes are the problem, it's because we have this weird property with flash memory where we have another operation called erases. So writes can only happen to empty blocks. So we can't just write data to a block of flash memory and then write a different chunk of data to that same block of flash memory, overwriting the previous data. Instead, doing an overwrite is a two-step process. Step one, we need to erase a block of memory in order to generate a clean block of memory, an empty block of memory, where it's legal for us to do writes. And then we have to do the write operation. Now, the write operation is pretty quick. But erases, to get us from a dirty block of memory that has been written to a clean block of memory that we can write to, have some complications. So the first complication is that erases happen in big chunks, bigger than the system block size. And for the purpose of the example that we're going to look at in a second, I'm going to call this 16K. So we have, for this example, 4K pages and 16K chunks. So 4K pages or blocks that we're talking about here, and then 16K chunks, which is what we have to deal with for erases. And then in addition to erases not working on the same size object as reads and writes do, they're also really slow. To erase a chunk, it takes like 2 milliseconds, not microseconds like the read and write operations up here, but milliseconds. So if we want to erase 16 megs of data, that's suddenly going to take like a second of time on the hard drive. And so if we have to erase as part of our write operation, if we have to erase to overwrite a cell, solid state drives suddenly aren't that fast anymore. And so this results in us having to do some optimizations. There's also one more annoying property about erases. They're a limited resource. On QLC, which is the modern low-price flash memory that you will probably end up getting if you go buy an SSD right now and don't get the expensive one. You're talking about only around 1,000 erases per block ever. Once you've done your 1,000 erases on a block, that block can't erase anymore. That means that block can't be written anymore, which effectively means that block can't be used anymore. Maybe if you were at like 999 erases and you just left that block and never wrote to it again, it could last for quite a while. But chunks of memory die as the result of writing to them with NAND flash in general. And for modern SSDs, they die pretty quick because of the way we're using the technology. Older, lower density flash solutions, so QLC means that for every sort of cell of memory, they're trying to store 4 bits. And in order to store 4 bits, you have to store 16 different logic levels. And that means that as you get sort of imprecision from writes, from writes and erases, which is what causes this degrading. Imprecisions matter an awfully lot faster if you're trying to distinguish 16 values compared to distinguishing 2 values. And so in comparison, SLC, which is what we used in the first generation SSDs, that's single level of logic per cell. So sort of 16 different values per cell in 4 bits. At 4 bits, we have one bit per cell, so we need to distinguish 2 levels, just 1 or 0. Those could easily do 100,000 write erase cycles, and so those drives last an awful lot longer than the modern QLC drives do, although they were also much lower capacity, so depending on how you're measuring, maybe they didn't last that much longer, because if you have a 32 meg solid state drive and you write a gig to it, you're doing an awful lot more erases than if you have a 100 gig drive and you write a gig to it. So this is the sort of basic situation that we're stuck in for SSDs, and this means that the sort of obvious way to implement a simulation of hard drives with SSDs just doesn't work. You can't make it so that the logical block addresses that the software is providing to the hardware are the physical block addresses, the actual which flash chips, which flash chunks get used to write data. Because some data gets written more frequently than other data. There's files that get written constantly as you're using your computer, like the swap file. And then there's files that almost never get written. Say your desktop wallpaper options that got installed with your operating system. Those get written once, never get written again, and just sit there. And so if the swap file was always getting written to the same physical flash blocks, those flash blocks would be slow because they'd have to get erased constantly, and erasing is our bottleneck in performance, and they'd wear out. And with QLC and 1,000 erase cycles, when we start to do the math on how long things take, we can erase in 2 milliseconds. Doing this the sort of obvious way would destroy a solid-state drive in 2 seconds. So we can't do it that way, we have to do it some other way. And the way we solve this problem is with virtualized block numbers. In the same way that we do virtual page numbers for virtual memory, and we have a table that's going to map the page number that a user program sees to the physical page number that's actually going on in RAM, solid-state drives have an internal lookup table that is going to map the logical block address, logical block number, that software is providing to a physical block number. And this allows 2 optimizations to happen. The first optimization is wear leveling, to try to make it so that the physical blocks, we are going to try to spread around erases across all the physical blocks. We don't want any physical blocks to get all of the erases, but we also don't want any physical blocks to get none of the erases, because erases are a resource and we'd like to take full advantage of the resource that we have. And so by doing this sort of wear leveling, we can make a like 1 terabyte QLC SSD look like we can do 1,000,000 block erases instead of being able to do 1,000 erases of a block, and suddenly the device is actually useful and isn't just instantly destroyed in 2 seconds. The other thing that's going on is that we can try to make sure that we always have a pool of empty pages available to write to, empty blocks available to write to, so that we never have to have a user program waiting on this 2 millisecond erase latency. We're okay with user programs waiting on the hardware write latency, although we're not super okay with that either, and we'd rather put a DRAM cache on our SSD. Most non-super cheap SSDs have a DRAM cache so that they can try to buffer that write so that it looks even super faster than it is. But by doing garbage collection in the background and trying to find things that can be rewritten so that we can erase as much as possible and keep as much free space as possible, we can have the SSD try to make sure that there are free pages available to do writes, and so the user doesn't see the 2 milliseconds of latency. That does mean that occasionally you'll get lag spikes with an SSD where this sort of garbage collection and erasing didn't keep up, or you didn't have enough free space to make it work. And as a result, you will actually see this cost that is innate to the hardware, but usually you can avoid it. The one thing that is the recommendation to try to avoid it as a user is to never fill an SSD all the way. Filling an SSD 80% is good. Above that, probably better to get another SSD just for performance reasons, so that you aren't getting super tight as far as free space goes, and the SSD firmware can do its job. Now, with all of that, this raises the question, how does the performance optimization plan for SSD differ from the performance optimization plan for hard drives? The plan for hard drives was just avoid random access like the plague. For SSDs, it looks like we don't really care about the difference between random access and sequential access, but for some technical reasons involving interfacing and drivers, that ends up being still sort of the most significant thing that as a file system developer you care about. So as long as you have a SSD controller with firmware that's going to do wear leveling and garbage collection and stuff to try to mitigate these properties of the flash memory, still the most significant thing that you can do for SSDs is try to do sequential writes instead of random writes, try to do big writes instead of small writes, And it turns out that those are the things that you wanted to do for hard disks. So the optimizations for hard disks still work on SSDs. They're just not as huge a deal anymore. The disadvantage of not doing that optimization is going to be a factor of 10 or maybe a factor of 100 instead of, well, more like a factor of 10. It was a factor of 100 for hard drives. So that's the story with SSDs. And I'll be back in a second with our third topic for today, which, our third example of storage for today, which is something that we don't quite have yet, but is something that we may have in the future.